So we talk a little about sensors and this P5. This is actually a summary of a chapter or an article that is actually being published this month in Sensors and Materials. I've kind of uploaded it into your folder if you want to read the detailed statement on this. So P5 medicine. P5 actually derives from Leroy Hood's description of P4 medicine, which is that healthcare would be personalized, that healthcare will be predictive, that it would be participatory, where people actually engage in their own healthcare and preventive. And to that, of course, importantly, what happens at a societal level, it's a kind of has a public health perspective. So it is a patient-centric way of providing health, and it is also seen from a public health lens. Now, with P5 medicine has also come a transition from the very hospital-centric way of providing care to moving to specialty labs, to outpatient clinics, community, and eventually the patient. And to be able to develop personalized care, the kind of health systems that we have in mind presupposes access to sensors, point of care technologies that will allow biometrics on the patients to be collected, often in their own native environment. Now, that is fundamentally changing the way we provide care from a reactive type of medicine that is delivered inside of hospitals to a more preventive type of medicine that takes place in the patient's home and is driven by the patient. So it is a growing emphasis and a change from disease to wellness. Now, in talking about point of care technologies in particular, which I will focus on in my talk, I have to emphasize that when I talk about point of care technologies, I'm actually speaking to devices or technologies that are in the field, either in the community clinics and or the patient's environment, and less so in the hospital, though you could do the same thing. For example, a HIV testing done in the hospital setting is not so much a point of care as something that is done in the community clinic, where it is used to make the final treatment decision. And so there are different utilities and different economies involved in different aspects of this healthcare continuum. The highest value proposition is actually in resource poor settings, and we have Idogen. I thought I saw him. Oh, you're there. Oh, you're so blended with the. So he will talk about this. Sorry, I didn't say I saw you here. So and he will talk in greater detail. He does some very fascinating work, and I offer my perspective more from an end user as a clinician confronted with the problem, and I will give you some operational definitions of some of the terms we use in point of care technologies, and a little snippet into an insight into my journey and how I have worked with technologies to come up with solutions. Hopefully, there are some insights that are useful to you. Now, with point of care technologies, there are two terms you need to know. One is biological markers or biomarkers, and the other one is biological sensors. When we talk about biomarkers, we usually think about cells or molecular alterations, but we often forget the physiological metrics are also very important, like heart rate and heart rate variability. Those are also biomarkers. And biological sensors or biosensors are anything, these are compact devices that measure and detect and measure these biomarkers. There are two essential types of biomarkers, one of exposure, and the other one is biomarkers of disease. So biomarker of exposure is actually, for example, if somebody has lead exposure, instead of the conventional way of capturing historical data, one would then look at the levels of the toxin in either the blood or the teeth or their nails. and that gives you a distinct quantifiable level of what the exposure, internal exposure of that subject was, and also allows you to think about the potential health consequences. So it's a biomarker of exposure. It helps you predict risk. And then there are the biomarkers of either screening or diagnosis or monitoring. And very early on, before there are any symptoms, or when symptoms have just established, or finally to look at the progression of disease or its response to therapy. So it's not that this whole point of care technology or approaches are new. It's the ancient Greeks, the ancient Chinese and Indian physicians were aware of it. Their glucose showing up in urine was a good sign of what was presumed to be diabetes. Fortunately, due to our technologists and engineering friends, we no longer have to worry about, every time we meet our patients, testing out their urine. We have, so this would be a biosensor for urine. This is a very common biosensor that is used, the blood glucose monitor. And it doesn't necessarily, they give us a quantitative readout on a gradient, but that doesn't necessarily need to be the same. A pregnancy tester, a yes, no, is also a biosensor, and probably between the blood glucose and the pregnancy test, they are the most, probably 95% of the commercial market out there. And then there are these biosensors patches that you apply, and Santosh will speak about it. This is a smart patch that people apply to the chest. It looks at heart rate variability, respiration, and so on. So the term biosensor does cover a whole gamut of these technologies. This is usually the operation framework. The data that is collected, acquired by these biosensors, be it attached or detached, is then picked up by a local data acquisition node, like a smartphone, and then it is transmitted. That information is transmitted to a health system where then it is analyzed, and then either the emergency room or the journalist or specialist is alerted, and even eventually friends and family. And eventually what happens is just-in-time adaptive interventions would be pushed back to the patient. Now, there are different types. One is the continuous monitoring, and Santosh will speak about it. And then there is the episodic monitoring, where we are essentially taking snapshots. And that's what Aidogan and I will be covering in some detail. For point-of-care technologies, there are many different reasons, but the most compelling reason is the immediacy of the result and the lack of errors that creep in due to handling of the material. So when a healthcare person meets with a patient is often like a black box. They're driven by it's kind of a syndromic approach. You ask the history, you get the symptoms, and you make some inferences. And obviously, at that time, you may need to take a biological sample and send it off to a lab. When that happens, the first thing, the sampling, there are issues of contamination, the specimen handling. You need specialized personnel. You may need a phlebotomist if you're getting a blood sample, and then you transmit it. And at that time, the specimen can degrade, or it can even get lost. At some point, it reaches a highly specialized lab with very expensive equipment. And then there is mishandling, there is equipment costs, and there are labor costs. At that point, the results are derived, and then there is misreporting and lost results. And eventually that comes back to the healthcare provider, who then makes a more informed decision to manage the patient. Unfortunately, in the real world, this turnaround time can be days to weeks. Usually the physician encounter, for example, is 15 minutes. And in that time, it is very rare that they have access to these lab values. Or out in the community, say sub-Saharan Africa, where malaria is a huge problem. 3 million people die every year from it. And when they take the blood test they have to treat it empirically based on the syndromes, and that leads to a lot of over-treatment. And so the conventional things like chloroquine and all no longer are effective. So they have to take the blood smears and send it to a specialized lab. You depend on someone with a motorcycle to transport it to a central lab. And unfortunately, by that time, the results come, the patient has long gone, long disappeared or died. So the turnaround time is a very critical fundamental issue that drives this whole point of care technology. With a biosensor, that can be reduced to minutes. And if that can be achieved within that 15-minute often interaction that you have with the subject, that informs the clinical decision making, and it's a much more focused and data-driven management of that clinical condition. At its very essence, there are three elements, and I'm going to make some generalizations here. A biosensor has a recognition element, it has a transducer, and it has an electronic system which gives a feedback to the patient. The recognition element is usually a bioreceptor. It could be an antibody, it could be an enzyme, it could be a nucleic acid. The transducer, there are many different types. And then the electronic system is an amplifier or a processor display. It can be very complex and very elaborate. So what happens when exposed to a biological fluid with the analyte of interest, it kind of binds to the bioreceptor and it causes a change. That change is detected by the transducer and converted into a signal, which then is picked up, it's cleaned, it's analyzed, and then it can give feedback to that patient. That would be a kind of a idealized biosensor. Now, these biosensors are simple, and the way you approach these biosensors is they should be like black boxes, very easy to use for the end user. But what they do and should do is hide the whole complexity of all the elements that go into it, from collecting the signal, transmitting it through the data acquisition mode to the central database where it is merged with the electronic medical record, where there are data. There's a data analytic component to it, and then there are dashboards, and it goes back. So all that is usually hidden behind this whole infrastructure that hides behind a biosensor. When you think about biosensors, if you're going to use it in your research, there are some critical elements that are necessary. One is, of course, the accuracy, that it has to be give a very accurate readout. Now, I must caution you that these biosensors are actually surrogates of these highly elaborate centralized lab equipment. So they will never be, it's very difficult to be accurate as a highly evolved lab. So there are some trade-offs in accuracy, but by and large, accuracy is a very fundamental value of any biosensor. Then, of course, is it reliable? There is always a drift with this equipment, but it has to give you more or less reliable results. If you take it over days, months, and there are different ways of approaching it, but reliability is also an essential element. Sensitivity, the lowest concentration of the analyte that it can detect and measure. It has to be very specific, and antibody-antigen reactions are quite specific in that sense. But there are challenges, particularly when you're doing multiple of these, multiplexed assays, because there are issues of cross-reactivity, and I'll get into that in a moment. And most important also, it needs to have that dynamic range. If you're looking at a certain, say, blood value, you should have a biosensor that takes both the healthy and the diseased part of that range of values that you would get and capture the entire range. And so those are some essential elements of a biosensor when you think about using biosensors. Now, obviously, it has to be rapid. The faster you get it, the better off you are. And again, like I said, the 15-minute encounter is usually that definition, time constraint that you would want the biosensor to work under. Low cost. Obviously, you want them to be low cost. They can be used particularly in low resource settings. And when you think of cost, you should not just think of the biosensor, but you should also think about the amount of time that is used, the complexity. Can it be done by a fully trained, low-level primary care worker? Does it need very elaborate refrigeration? So even lancets and all, those are all things that factor into the cost. So it's not just the cost of the biosensor, but what it takes to operate it in the field. It has to be user-friendly. like I said, don't make complex, think not of making complex biosensors that open. It should be able to be used by, simple yes, nos. It has to be as user-friendly as you can make them. Obviously, it has to be small and portable. You cannot call a tabletop equipment a point-of-care technology. While it is, in a way, what you're thinking of is a small little device that can be carried around with ease. Nanosensors and all are clever, but you don't want it so tiny that you cannot find a biosensor when you need it. And they have to be robust, particularly, and Idogen will talk about this, particularly when you go into low resource settings. Sub-Saharan Africa, think about the extremes in temperature, the lack of refrigeration. So it has to be able to withstand manhandling or mishandling. The other important key thing, again, is because of the drift, calibration is if you're going to use the same thing again and again, particularly the reader, it should be some kind of self-calibration. That is something that is done every day with centralized lab equipment. So let me kind of give you my narrative of how I kind of used it. I was always I was intrigued, treating people with facial injuries. I was kind of intrigued. It's a kind of an unfortunate, pretty common thing, particularly in large urban centers here. And usually the surgical approach is you restore form and function, and that's the end. 1 month patient looks good, go home, end of story. But I was kind of more interested in what really happens to these people after that. It's a grievous injury, and it was quite clear early on that there are mental health sequelae that are never asked by the surgical team, and what does happen, as we know now, is that there is always a traumatic psychopathology, particularly in the people who are prone to those things, particularly vulnerable populations. And a small subset of them do develop conditions like post-traumatic stress disorder, depression, or substance abuse as coping skills. The challenge, if you are in a trauma setting, is that these early stress reactions that may give you a sense that this patient is not handling that traumatic stressor quite well, they're very subtle. And to me, particularly coming from the physical world of putting things together, this whole syndromal approach was very perplexing. The DSM is like, it was very difficult to understand. So many different symptom clusters that kind of overlap onto each other. And most importantly, in the trauma setting, you don't have that kind of time and patience to do these extended, something like the CAPS, which can take a whole hour to administer, that screens for post-traumatic stress disorder. And so that kind of got me thinking, maybe there are alternate ways of approaching this in a much more quantifiable manner for people who are non-specialists, non-psychiatrists, or non-psychologists. So when we are confronted with a traumatic stressor, there is a neurobiologic response, and that stressor releases a whole bunch of enzymes and hormones into your body, and this actually manifests. Some of it manifests in our peripherally in biofluids like blood, sweat, tears, and even saliva. And my goal was, working with technologists to figure out ways to create these point-of-care devices that can measure, analyze, and eventually report back to the patient and the care provider, and be able to identify people who are, undergoing a acute stress reaction and/or stay sustained in that mode that will predict post-traumatic stress or eventually depression. Now, a key choice that you'll have to make is a choice of biofluid. And in my case, I found very early on when I began, I would I'd do blood draws, and then quickly found out that this tough macho men, and most of the trauma gunshot wounds are men, 95% of them, and these macho men would take bullets, but you showed them a needle, and they would never come back for the follow-up. So it was messing up my exquisitely detailed repeated measures design, and I'd increasingly, resort to my clever statisticians who would come up with multiple imputations, like if they're shown up, then this is what they would have said, and it was getting too complicated. So blood, I had to rule out, and so I ended up with saliva. This is something that people easily give, and there is no embarrassment with it. There is none of the drama of blood. There is none of the emotional appeal of tears or the sincerity of sweat. But saliva as a medium is what I focused on. And just to give you an idea, so I hooked up with a group that was working, also interested in saliva, and they had a connection with a company. The other thing I found out is most US companies were not interested in making biosensors. They wanted immediate returns. If they put some money into doing something, they wanted to see a large market share of it. And anyway, so this group in Japan had access to a large company that was willing to do those prototypes for them. So this, in a sense, is what we come up with: a collector pad that is placed under the tongue, and then it's placed there for about 15 minutes, and then placed into the biosensor, which then gives a readout. What we do is we take the readout and map it onto the clinical assessments of the stress response, and then working with the statisticians eventually come up with these integrative algorithms, which would be then placed into the CPU of the biosensor, and so you would have a more informed readout, like this patient is at a high risk for a certain condition or a low risk for condition. Now, this is where it gets interesting, because this is where the whole multidisciplinary thing comes. Things like product design. Suddenly we had to think about collectors that would collect a fixed amount of saliva that saturates. There's a little pad there, and it saturates with a fixed amount of saliva in 10, 15 seconds. So then you have to have, obviously, people who collect saliva in the clinical settings. To make the biosensor, one needs biochemistry, microfluids, integrated circuits, rapid prototyping, which is where the company comes in, and then there are the psychometricians, particularly for us to help me with figuring out ways to score the PTSD and depression, and then of course there is study design, and finally bioinformatics. So you can see that suddenly my aspirations, when fleshed out, have become very complicated and needing a lot of different expertise. This was the first one that we focused on, salivary alpha amylase. It's a common enzyme in saliva, and it is a surrogate for the sympathetic response. This was the biosensor. These are disposable strips that you place under the tongue for about 15 seconds, place it in the biosensor. The first one that we made was colorimetric, meaning it changes color when the enzyme acts on the substrate, and the intensity of the color reaction is then read out. It took fixed amounts of saliva. It has day and time stamps, so you could collect store data for up to 6 months on it, and it had algorithms that would normalize for slight differences in pH of saliva and the ambient temperature. And some of, then of course you have to look at accuracy. What we do is then we take saliva samples, compare that to a standard lab Olympus analyzer, and just to give a sense of, we spike saliva with increasing concentrations, and then you can see within the dynamic range, the working range, there is a good correspondence and there is a linearity. Then the question is, can you, using the same saliva, would you get similar results? So we took saliva samples, and then about 6 weeks apart with 3, different machines, repeated that, and essentially you can see there is a variability. There's a coefficient of variation of about 8.4, and that is acceptable with point-of-care technologies. There is always going to be a trade-off, and that is for point-of-care technologies acceptable. Then the question was, how much of the variability was the biosensor actually contributing? There is a natural variability in the human subject population, And so through interclass correlations, we found that, it was about 3% that could be explained, meaning that the noise given by the biosensor would be about 3%, which is the same more or less as the random error. So most of it is really the variability of alpha amylase in the subject population. Similarly, for cortisol, we had to get into another type of immunosensor. This was made by the prototype made by Rome Corporation. Again, it's a little larger. We did a similar set using the ELISA assay as a comparator. Again, we get a good concordance with the standard large lab-based equipment. Now, typically what happens, in simpler times, you can make use of single biomarkers. HIV is a good example of a single marker disease. PSA, not very, now we are less favorable, but it lets you track, prostate, track prostate cancer or cancer antigen 125. No, but increasingly what has happened, recognizing that, for example, cancers, neurodegenerative diseases are much more heterogeneous in origin. So the field of point-of-care technologies are moving towards multiple biosensors, even if by themselves any one has low sensitivity and specificity, but that combinatorial power increases dramatically the sensitivity and specificity of that panel of biomarkers. So in our case, I was interested in a trauma panel. This is work that's funded by NIDCR, and David Elishoff and others are helping. So what we do is we look at different pathways in which the stress response expresses itself, and then we take domain knowledge-based markers that have been researched and put together, and what we're doing is collecting saliva samples on these trauma patients and hopefully be able to articulate a panel of these biomarkers that we can then use to functionalize these biosensors that are being developed. Concurrently, also keeping an eye on the bioengineering world, we kind of began with carbon nanotubes. Collaborator of mine, we essentially took these very small, thin single-walled carbon nanotubes, functionalized them first with alpha amylase and then with cortisol. The advantage of this is you don't need multiple labeling techniques, which are quite elaborate. And so when it binds to the alpha amylase, the resistance changes, and that is read out. And the goal is to kind of create these high density arrays that can let you look at multiple markers on the same kind of chip, and it has control wires that can, control for errors. We are on the lookout, as we are developing these platforms. More recently, working with field effect transistors, and the field is always changing, and so right now we're looking at FETs, seeing if they can be used to create these multiplexed assays that are actually very low cost disposable.